When we feed data into a standard machine learning model, the architecture is almost always designed to produce a single, high-probability output. It takes a complex set of variables and collapses them down into a clean, confident metric, like a 99% match. In controlled environments, like image sorting or text prediction, that single score is highly efficient. But apply that exact same architecture to biological classification or public health triage, and that mathematical collapse becomes an epistemological hazard. Forcing a single confidence score requires the violent erasure of context. The model mathematically discards expert disagreement, filters out critical geographic variables, and smooths over morphological contradictions to output a single decisive answer. There is a widespread industry demand to make generative AI more accurate by eliminating hallucinations and forcing consensus. But demanding absolute certainty from a statistical model misinterprets how scientific review actually works. Science relies on navigating ambiguity, not erasing it. By stripping away the underlying uncertainty to present a clean result, the model stops acting as a computational tool. It assumes the role of an autonomous scientific authority. This is Synthia. It is an educational research codebase built specifically to reject that autonomous classification model. Rather than acting as a truth generator that spits out definitive answers, Synthia functions as an indeterminacy preservation engine. Its entire architecture is designed to map and remember exactly what we do not know. Synthia operates within a much larger framework known as the SecuredMe Ecosystem. This network enforces strict governance over how biological and taxonomic data is handled. The architecture here relies on structured containment. The system places hard boundaries around the core data, locking down the parameters rather than allowing a generative network to interpret data freely. Inside this ecosystem, generative AI is restricted to acting strictly as a semantic router. It can read and route natural language requests, but it must delegate any formal scientific conclusion to external verification engines and human experts. To map uncertainty, Synthia separates its calculations into two layers: pure engine math and biological system math. In the pure math layer on the left, the system uses a nutrosophic vector. Instead of a single probability score, it calculates three completely independent values for any given data point: its truth, its falsity, and its indeterminacy. When that math hits the biological node on the right, it maps directly to physical evidence. The I-System-S state identifies where conflicting morphology, divergent habitat reports, or expert disagreement prevent a single result, measuring physical system instability through a mathematical lens. A high contradiction load in a purely abstract algebra exercise is just a mathematical state, but a high contradiction load surrounding a local habitat observation or a contaminated milk batch carries immediate physical consequences. By contextualizing that indeterminacy, the system triggers a mandatory halt. It stops attempting to classify the object and immediately structures a required human triage event. Before Synthia ever attempts to analyze a biological specimen, it first measures the instability of the language used to describe it. This chart shows the nodes pulsing as the system calculates lexicon entropy and decision gap uncertainty. It measures exactly how fractured the existing scientific literature and definitions are before making any moves. During the first three phases, this data builds a graph review layer. Those thick lines represent recorded expert disagreements and morphological contradictions, mapping out the messy reality of the biological data. The final output of this layer is not a confident species match. It compiles a structured phyloplithogenic review packet. The AI identifies the specific bounds of a scientific debate, presenting the conflicting parameters directly to human experts for resolution. Moving into phases 4 and 5, the system enforces a set of strict algorithmic and evidence guardrails. To prevent data pollution, the architecture explicitly rejects massive, unstructured data feeds like raw sequence alignments. The filtration criteria mandate that only highly compact similarity summaries and curated genome anchors are permitted to pass through the barrier into the core logic. The system also audits its own behavior. Parameter choices like regularization, validation folds, and stopping criteria are logged and firmly attached to the data packet. These algorithmic settings are treated strictly as visible conditions of the output. They are exposed for human review, never presented as an absolute guarantee of biological truth. Phases 6 and 7 construct the scientific governance and evidence reporting layer. Every data point must satisfy rigorous metadata requirements to prove its origin. This ensures the dataset provenance is permanently embedded in the final report. The system emits specific, standardized tracking formats. It maps Prov-O entities and generates RO-Crate research object manifests so that any researcher can trace an output back to its original node. We have to explicitly clarify the boundary of these exports. Generating contributor roles or formatting DOI registry metadata does not confer copyright reuse, and it certainly does not create formal taxonomic authority. Implementing this level of provenance tracking ensures that every piece of biological evidence remains visible, completely auditable, and entirely subject to human scientific governance. Synthia does not exist in a vacuum. This diagram shows the massive, gateway-routed SecuredMe ecosystem, which directs traffic through centralized hubs to specific endpoints like Codex, AMS, and Cerebrum. This broader ecosystem enforces strict IT governance rules. For instance, in official classroom settings, the use of local environment variables, hidden secrets, and raw API keys by students is explicitly prohibited. To maintain security and traceability, all workflows rely on containerized execution through Docker, heavily encrypted local records, and fingerprinted session approvals through secure browser gateways. In modern research, the integrity of the network and the rigor of the science are inextricably linked. Administrative safety creates the environment for scientific truth. The entire SecuredMe ecosystem is built on a singular foundational rule. It is designed specifically to prevent generative AI from making autonomous decisions. Its true utility is scaling the traceability of scientific disagreement, segmenting and categorizing knowledge rather than burying it inside a monolithic black box. The technology industry obsesses over building systems that generate smooth, confident answers at all costs. Real science requires the map creates errors in complex systems. Preserving the precise shape of our ignorance ensures that every biological conclusion remains subject to verification and human review.